There are two objectives in this section. First, use Gaussian elimination to solve the system of linear equation. Use matrix equation to solve the system of linear equation. A linear equation is an equation that can be written in the form ax plus b equal to c, or ax plus by plus cz equal to d, or a similar form with more unknowns, where a system of equations is set of more than one equation. Solving a system of equation means finding all order pairs xy, or order triple x, y, z, and so on, that will satisfy each equation in the system. Geometrically, this means finding all points that are on the graph of each equation in the system. Look at this system. Why we call this as a system? Because it is a set of two equations, and each equation is of the form ax plus by equal to c, with two unknowns, x and y. The order pair 1, 2 is a solution to the system, because 1, 2 satisfy each equation. For example, we substitute the 1 into x and 2 into y for the first equation, so we have 3. And for the second equation, 2 multiply 1 plus 3 multiply 2 equal to 8. So we say this point satisfy this system, and this point is a solution to the system. Does this system have any other solution? We can convert the two linear equations into the slope-intercept form. Because in this form, we can identify the slope immediately. The first equation is the equation of a line with slope -1 and y-intercept 3. For second equation, the slope is -2/3 and the y-intercept is 8/3. Because the slopes are different, the lines are not parallel and intersect in only one point. So 1, 2 is the only solution to this system. It is the point at which the two lines intersect. A system of linear equation does not necessarily have one solution. Consider a system of two linear equations in which each equation has two unknowns, x and y. Geometrically, solving such a system means finding all points where the two lines described by the two linear equations intersect. Two lines can intersect at no point, at one point, or at an infinite number of points. This case is for two unknowns, two linear equations. The possible result may no points, one point, infinite number of points. A system of two linear equations with three unknowns x, y, and z describe a set of two planes. Two planes can intersect nowhere along a line, but not a single point. So the system can have no solutions or an infinite number of solutions, but not a single solution. In fact, any system of linear equations that has fewer equations than unknowns will have either no solutions or an infinite number of solutions and never a single solution. A system of three linear equations with three unknowns x, y, and z describe a set of three planes. Three planes can intersect nowhere, at one point, or along a line. So the system can have no solutions, one solution, or an infinite number of solutions. In fact, any system of linear equations that has as many equations as unknowns will have either no solutions, one solution, or an infinite number of solutions. Look at the first objective. For these simultaneous equations, we can call this as system because we have three equations with three unknowns x, y, z. And this system can be written as this form. And this form we call matrix equation. Ax equal to b, where the matrix A is the coefficient of x, y, and z for each equation. And the size of the matrix A is 3 by 3 matrix. And the matrix X is a 3 by 1 matrix. And its unknowns for these three equations x, y, z. And the matrix B is 3 by 1 matrix and is a constant of these three equations. And this matrix equation, this system, can be solved by using Gaussian elimination. In Gaussian elimination method, our purpose is to use row operations to transform an augmented matrix into a row echelon form. In linear algebra, a matrix is in row echelon form if all non-zero rows are above any rows of all zeros. The leading coefficient of a non-zero row is always strictly to the right of the leading coefficient of the row above it. This is an example of row echelon form. In Gaussian elimination method, it will be easier if we follow a systematic procedure to obtain an upper triangular matrix. From the augmented matrix, this is the augmented matrix. In order to get the upper triangular form, we should transform A2, A3, and B3 to 0. A2, A3, and B3 to 0 in the anti-clockwise direction. So this is an anti-clockwise direction. A2 first, and then A3, and the last one B3. Then the row echelon form obtained. And these three zeros we call upper triangle. So from the row echelon form, we can form three equations to get the x, y, z unknowns. But look at the first equation. The first equation is with a z unknown. So, meaning that we solve the z unknown first, then y unknowns and x unknown. So, this method we call backwards method. Possible solutions to a system of linear equations if the row echelon form has a row of the form where c is a constant, then the system of linear equation ax equal to b has no solution. If the row echelon form has a row of the form where the whole row is equal to 0, then the system of linear equation has infinite number of solutions. If the row echelon form does not have the form in A or B above, then the system of linear equation has unique solution. Only one solution. Look at the first example with star. Using Gaussian elimination, solves the simultaneous equation. We also can call this as system because we have three equations and three unknowns. First step, convert this system into the augmented matrix. So, this is an augmented matrix. Your left side is coefficient of x, y, z for each linear equation. And your right side is constant for each linear equation. Before we perform the elementary row operation, you should identify the coordinate of each element. The 2 is a coordinate of A is element, first row, first column. -2 is an element of first row, second column. 1 is an element of first row, third column. And this 3 is an element of second row, first column. And 1, second column, second row, second column. And so on. A, 2, 3, A, 3, 1, A, 3, 2, A, 3, 3. After you have identified the coordinate for each element, so your first step is you have to convert these 3 to 0. Remember, when we perform the elementary row operation, we should follow the procedure, the systematic procedure in anti-clockwise direction. So your first element to be changed to 0 is 3. And then 1 and -3. So look at the 3. The 3 is the element of A21. the coordinate for this tree is second row, first column. So you write the formula. You can see the tree is at the 2 and 1. So we just use the row 2 and row 1. Write R2, R1 and replace the new row R2 into R2. So now your R2 is 3, 1, negative 1. Row is R represent row, the whole row. R2 is 3, 1, negative 1 and 7. R2. R1 is 2, negative 2, 1, 3, the whole. Now I just want to change this 3 to 0. Then my output I replace into second row. How to produce 0? My R1 is 2. So I need to multiply 3 over 2 into the first row and then minus. Look at the 3 over 2. So we have 3 over 2 here. Take 3 over 2, multiply the whole R1. 3 over 2 multiply 2 is 3. 3 over 2 multiply negative 2 is a negative 3. 3 over 2 multiply 1 is 3 over 2. And 3 over 2 multiply 3 is 9 over 2. So in order to get the 0 here, I should put a negative. 3 minus 3 is 0. 1 minus negative 3, 4. Negative 1 minus 3 over 2 is negative 5 over 2. 7 minus 9 over 2 is 5 over 2. So this will be my new R2, the whole second row. So this is my formula. In next page, we have calculated the new value for R2 in previous page. So the augmented matrix can be written as this form. The first row and the third row are remain. Just replace the R2 by new value. Now the next step is convert this one to 0. Identify the coordinate of this element 1. The coordinate for this one is third row, first column, 3, 1. So immediately write the formula. You should create your own formula. R3, 3, 1, R1. Replace into R3. Then your R3 is 1, negative 3, 2, 0. R3 is 1, negative 3, 2, and 0. And R1. R1 is 2. How to convert this 1 to 0? Here you should produce 0. 1 minus 1 can produce 0. So here should be 1. So how to convert this, the first row, the element 2 here, to 1? You just need to divide by 2. Half multiply 2 is 1. Half multiply negative 2 is negative 1. Half multiply 1 is half. And 3 multiply half is 3 over 2. So how to get a 0? There's only 1 minus 1. So we perform the minus operation. Negative 3 minus negative 1 is negative 2. And 2 minus half, 3 over 2. 0 minus 3 over 2, negative 3 over 2. So this is new R3, the new value for R3. First row, second row remain. The value here substitute into R3. So look at this the matrix. We already have 2, 0. And the next element is negative 2. We have to convert this negative 2 to 0. So we will get row echelon form. The coordinate of this negative 2 is third row, second column. Third row, second column, R2 should replace into third row. R3, 0. Negative 2, 3 over 2. And negative 3 over 2. And R2. The R2 value is, okay, for this column is 4. But here is negative 2. Here is negative 2. How to produce 0? It's positive 2. Then 4. How to convert the 4 to 2? We divide by 2. So half multiply R2. Half multiply 0 is 0. Half multiply 4 is 2. Negative 5 over 2 multiply half is negative 5 over 4. And 5 over 2 multiply half is 5 over 4. And how to get a 0? Negative 2. Here should be plus. Because negative 2 plus 2 is 0. So 0 plus 0, 0. 3 over 2 plus negative 5 over 4 is 1 over 4. And the last one, negative 3 over 2 plus 5 over 4 is negative 1 over 4. So this value is replaced into R3. So we obtain row echelon form. And 3, 0 here we so-called upper triangle. And from this row echelon form, we get the z value first, and then y, then last one is x value. So we start from the last row. And you know that the coefficient here is actually is for x variable, and the coefficient, this coefficient 0 is actually for y variable, and the coefficient here 1 over 4 is for the z variable. So for the first equation, you can write down the first equation is 1 over 4 z equal to negative 1 over 4. And the second equation is this one, 4y minus 5 over 2 z equal to 5 over 2. And the last equation, 2x minus 2y plus z equal to 3. Look at the next page. The first equation, the second equation, and the third equation from row echelon form. So from the first equation, you can get the z value. The z value is negative 1. After you obtain the z value, you substitute into the second equation. Then you get y value. After we have y and z value, we substitute into the third equation and get x value. So the answer for this system is x equal to 2, y equal to 0, and z equal to minus 1. You can substitute this value into our system to verify the answer. For second objective, we call matrix equation. The method used in second objective also can be called as inverse matrix method. Consider the system of simultaneous linear equation with two variables x and y. So we have this system where a1, b1, c1, a2, b2, and c2 are non-zero constant. Then this system can be written as matrix equation ax equal to b, where the matrix A is 2 by 2 matrix because there is just only two equations with two unknowns. Look at the matrix A, A1, B1. They are the coefficient of x and y for the first equation. And A2, B2 are the coefficient of x and y in second equation. And the matrix X is 2 by 1 matrix. It's the unknowns for x and y. And the matrix B also is a 2 by 1 matrix. It's a constant of first equation and the second equation. After we have written the system into matrix equation Ax equal to B, and in order to solve the unknown for the matrix X, both sides we can put the inverse matrix A. Or in other words, we say we move matrix A to right side. So we have X, the matrix X is equal to inverse matrix of A multiply matrix B. If AX equal to B is a matrix equation where matrix X is an unknown matrix and the inverse matrix of A exists, then the solution is matrix X equal to inverse matrix of A multiply matrix B. Finding the inverse of non-singular matrix using elementary row operation. Here are the steps to find the inverse matrix using elementary row operation. Elementary row operation can transform an augmented matrix into a row equivalent matrix if any of the following row operation is performed. Two rows are interchanged. A row is multiplied by a non-zero constant. And the last one, a constant multiple of one row is added to another row. This operation we have performed in the previous example, where we convert the element to 0. The arrow here means replace. The following example illustrates the use of the elementary row operation for finding the inverse of a non-singular square matrix. To perform the elementary row operation, a systematic procedure to follow when carrying out elementary row operations. Look at the sequence. 1, 2, 3, 4, 5, 6, 7, 8, 9. Look at the second example. Given a system A, write it in matrix equation AX equal to B. B, find the inverse matrix of A using the elementary row operation. C, solve the system. So, from this system, you know how to convert it into the matrix equation. Look at the solution. So, for the A part, the matrix equation is AX equal to B, where the matrix A is the coefficient of x, y, and z for each equation, and the matrix B is unknowns x, y, z, and the matrix B is constant for each equation. Now look at the B. To get the inverse matrix, first you need to write your matrix A on left side and identity matrix on right side. And you should transform all the elements here to be identity matrix. So your right side will be inverse matrix of A. Now, follow the systematic procedure. The first element is 2. So you should convert the 2 to be 1. Call back, we have the operation 2 rows are interchanged. So I interchange the first row and the third row. So my 2 will become 1. The first row interchange with third row. Now I have the first the first row here interchange with third row. So the whole row I put here, and the third row I put at the first row. So my first element already obtained 1. And the second element is this 3. Follow the systematic procedure. The second element is this 3. I should change this 3 to 0. Look at the identity matrix. The element here is 0. So this 3 should be changed to 0. So to change to 0, recall back. You perform the elementary row operation to solve a system. In the first objective, the coordinate of this element is at the second row, first column. So you can write down first. The coordinate here is second row, first column. So R2, R1. Replace into R2. I show you again. Actually, they are same procedure. So R2 is 3, 1, 3, 1, negative 1. R2, 3, 1, negative 1. Zero, 1, 0. And R1, this is R1. 1, negative 3, 2, 0, 0, 1. Then the R1 is 1. The first element is 1. So how to produce 0? The value here should be equal to 3. Right? So I should multiply 3 for the whole R1, the first row. So 1 multiplied 3 is 3. Negative 3, negative 9. And 6, 0, 0, 3. Just multiply the whole row. And then I should perform the minus subtract. Because 3 minus 3, I will get 0. And 1 minus negative 9 is 10. And you calculate the rest. So we come up new output. This new output you should substitute into second row. And here's minus and 3. So that's why we have this formula, the operation. Now look at the next page. Replace this value into second row. After I calculated the new value for the second row, I replace the new value to second row. And the first row and the third row remain the same. Now, the next element is 10. So I need to convert this 10 to 1. The coordinate of this 10 is 2, 2. Second row, second column. And I immediately write 2, 2. So, now, to convert into 1, I just need to involve itself row. So the R2 is 0, 10, -7, 0, 1, -3. So I want to change this 10 to 1, meaning that I should divide by 10. So my R2, 0 multiplied 1 over 10 is 0. -7 multiplied 1 over 10 is -7 over 10. And 0 multiply 1 over 10 is 0. And so on. -3 over 10. So this is my R2. So I should replace this new value into second row. And the next element is these two. I should convert these two to 0. To 0, I should involve two different rows. So the coordinate of these two is 3, 1. So I write R3, R1, replace into R3. So just write down the R3 is 2, -2, 1. 1, 0, 0. And R1. R1 is 1. So we know that we should produce 0. Since the R1 is 1, so we should multiply 2. So 2 multiply 1 is 2. 2 multiply -3, -6. 4, 0, 0, 2. And we minus. So 2 minus 2 is 0. And -2 minus -6 is 4. You calculate for the rest. Now this is a new R3. And then the next element will be 4. We should transform this 4 to 0. And the coordinate here is 3, 2. Then immediately write R3, R2. Replace into R3. The R3 is 0. 4, -3. 1, 0, -2. And the R2 is 0, 1, -7 over 10. But we need to convert this 4 to be 0. Look at the second column. The 4 is at the second column. So at the second row, second column, the element is 1. So we need to multiply 4. Here should be 4. So we need to multiply 4. sorry, this one is R2. 4 multiply R2, 0, 0. 1 multiply 4, 4. And negative 7 over 10 multiply 4 is negative 14 over 5. 0, 2 over 5, and negative 6 over 5. In order to get a 0, so we perform minus. So this is a new R3. And we substitute into the R3. After we have calculated the new R3, so we replace the new value into the third row. Now the next element will be negative 1 over 5. And the coordinate of this element is at third row, third column. So R3, you write the R3, replace into R3. In order to convert this negative 1 over 5 to 1, we need to multiply negative 5. So look at the procedure. Original R3 is 0, 0, negative 1 over 5. Because we need to convert this negative 1 over 5 to 1, so we need to multiply the R3 by negative 5. So 0 multiply negative 5 is 0. And negative 1 over 5 multiply negative 5 is 1. And the rest, 1 multiply negative 5 is negative 5. 2 and 4. So this is a new R3. Now, the next element will be the negative 7 over 10. So the coordinate of this element is R2, second row, third column, 2 and 3. And replace into R2. First, write down the R2. And the R3. In order to convert this negative 7 over 10, the coordinate here is at the third column. So you observe the third column of third row is 1. So how to convert this negative 7 over 0, negative 7 over 10 to be 0? The only way is negative 7 over 10 plus the 7 over 10. So we will produce 0, right? So meaning that we need to multiply the R3 by 7 over 10. And we plus. So for the 0, multiply 7 over 10 is 0. And here also is 0. And here is negative 7 over 2. 7 over 5 and 14 over 5. And now we have 0 plus 0 is 0 and 1 plus 0 is 1. And the new R2 has come out. So we replace into the R2. And the next element will be 2. So the coordinate of these two is first row, third column. So you write R1, R3. Replace into R1. And the working still the same. You write down the R1 first. The R1 element are 1, negative 3, 2, 0, 0, 1. And the R3 0, 0, 1. Here is 1. And we know that we need to convert this to be 0. So since the element here is 1, so we need to multiply 2 into the third row. So we will have 0, 0, 2, negative 10, 4, and 8. And we perform the subtract so that the 2 minus 2 is 0. So 1 minus 0 is 1. Negative 3 minus 0 is negative 3. And here will be 10, positive, because 0 minus negative 10 is positive 10. So we have new and R1. After we perform, we get this 0, this element to be 0, and the last element will be this negative 3. And the coordinate for this negative 3 is first row, second column. So immediately write R1, R2. And you think about the constant to be multiplied for the second row so that the element negative 3 can be 0. So lastly, we obtain our left side is identity matrix. So right side will be inverse matrix of A. For the C part is solving the system. Since our system has been written in matrix equation, to get the unknowns x, y, and z, we move the matrix A to right side. Make sure in front of matrix B. This is because the matrix A is a 3 by 3 matrix. And sure, the inverse matrix of A also is a 3 by 3 matrix. And the matrix B, the size is 3 by 1. So it can be solved to produce 3 by 1 matrix. And the inverse matrix of A we obtain from B part. And we solve this matrix. And we obtain the value of x, y, and z. here are the guideline, the steps to find the inverse matrix. So let's say you are given a matrix A, either in the size of 2 by 2 or 3 by 3. The first step, find the determinant. So if determinant of A is not equal to 0, meaning that the inverse of matrix A exists. The second step, find the minor of each element in A, matrix A. And the third, write down the matrix of cofactor. And here is the formula. Write down the transpose of the cofactor matrix, which is the adjoint of A. So the adjoint matrix of A is transpose of the matrix of cofactor. And lastly, to get the inverse matrix, so it's equal to 1 over determinant A, where you get from the first step, multiply adjoint matrix of A. You obtain from fourth step. For the transpose of a matrix, if matrix A is an M by N matrix, where the I represent the row and the J is column, then the transpose of A, denoted by this symbol, and is given by AJI. Originally is AIJ, which is an N by M matrix. Look at the example. For this example, find the transpose of the following matrices. You have an A, B matrices. Now, you look at the size of the matrix A. The size of this matrix is 1 by 3. And the element here, the coordinate of this element is A11, A12, A13. Look at the answer. The transpose matrix of A is 2, 3, -4 in vertically. And you can see the size is 3 by 1. And the element 2 is A11. And the element 3 is A21. Element -4 is A31. For the B, this is a 3 by 1 matrix. And for the transpose of matrix B, the size of this matrix is 1 by 3. The coordinate of this element 3 is A11. The 5 is A21. The 6 is A31. After transpose, the element 3, the coordinate is A11. And the 5 is A12. 6 A13. So this is a transpose operation. For determinant of a matrix, a determinant is a real number which is associated with each square matrix. Let matrix A be an n by n matrix. Then the determinant of matrix A is denoted by, you can write the short form DET. So look at the example. Let's say the matrix A is a 2 by 2 matrix. Then, to get the determinant of A, first step, you write the round bracket. You convert the round bracket into modulus form. Then the second step, you put a cross. So, meaning that A11 multiply A22 minus A21 multiply A12. Notice that the expression on the right is the product of the major diagonal from upper left to lower right minus the product of the secondary diagonal from lower left to upper right. How about the 3 by 3 matrix? So for the 3 by 3 matrix, for example, we have this matrix A. So the first step, change the round bracket to modulus form. Here we have a sign for each element to calculate the determinant. Plus, minus, plus. For the first row, for the second row is minus, plus, minus. And the third row, plus, minus, plus. So look at how we calculate the determinant for this 3 by 3 matrix. First, you take the A11. The sign for the A11 is positive. You close the row and the column of A11. So meaning that you close the first row, close the first column. So you have these 4 elements left. Then you fill in here. And for second element, A12, refer to the sign. For the A12, it's negative sign. So you take the negative sign and then A12, take the element and you close the first row and second column. So we only have A21, A23, A31, A33. Then you assign here. And for the third element, A13, the sign for this element is positive. So positive value. And close the whole first row and the whole third column. So we have A21, A22, A31, and A32. You put them here, then you put a cross. For each. Then we back to 2 by 2 matrix. So A22 multiply A33 minus A32 multiply A23. And same operation for the rest too. Look at the example. So you are given matrix A in the 3 by 3. Find the determinant of matrix A. Again, I remind you convert this round bracket into modulus form, and you can use short form DET. So the first step is you take the element 1. The first element is positive sign. Then you close the whole row and the whole column. So we have 5, 6, 8, negative 1. And the second element is 2. But the sign for this second element is negative. And then you close the whole row and the whole column of this element. So we have 4 6, 7, minus 1. And then take the third element. The sign of this third element is positive. Then close the row and column of this element. So we have 4, 5, 7, 8. And you put a cross. And we calculate, we will get the answer. The minor and cofactor of 2 by 2 and 3 by 3 matrices. Consider a square matrix A of order 2 by 2 or 3 by 3. The minor of element Aij, denoted by Mij, is the determinant of matrix. We base on determinant method. That remains after we delete the I column. The cofactor of Aij, denoted by Cij, and the working to calculate the cofactor value is, this is a formula. And you look at the example. Let's say we have matrix A. The size of this matrix is 2 by 2. The minor of element A11 is A22. Refer back to previous matrix A. So look at the minor of element A11. We close the whole row, the first row and the first column. So we have A22. And for the minor of element A12, so we close the whole first row and the whole second column. So we have A21. And you perform the same operation for the A21 and A22. So we have A12 and A11. For the cofactor, this is a formula, the method to get the cofactor. So the cofactor of A11 is given by -1 power to I plus j. The I is 1, row, first row, and the j is column, first column, here. And then multiply the minor of element A11. The minor of element A11 is A22. And -1 square is positive. Now look at the cofactor of A12 for this element A12. So the formula is -1 power to the I plus j. The I is 1 and the j is 2. And multiply the minor of A12. The minor of A12 is A21 from the above here. Then because of -1 power cube is negative, so we have negative A21. Same for to get the cofactor of A21 and A22. How about we have a size matrix is 3 by 3. To get the minor of the element A11, look at the first element A11. We close the whole first row and the whole first column. So we have A22, A23, A32, and A33. And we put into here, into the modulus form, and we use the determinant method we put a cross here, so we get the minor of and the A11. And same for the minor of the element A12. We close the whole first row and the whole second column. We have A21, A23, A31, and A33. And still the same, put a cross and calculate. So same for to get the minor of A13, A21, A22, A23, and so on. Use the same method. Look at this example. Given matrix A, find the minor and cofactor of each of the element. For the minor of 1, you close the whole first row and the whole first column. So we have 5, 6, 8, -1. Then we put a cross. And we have the value is -53. Then for the minor of 2, close the first row and also the whole second column. So we have 4, 6, 7, -1. And put a cross, so we have an answer, -49. And same for the minor of 3, and so on. After we have the minor for each element, so we can calculate the cofactor for each element. Use the formula of the cofactor. -1 for the first element 1. The coordinate for this one is first row, first column, I plus j. And the minor of this one is -53. And you calculate. So the value is -53. And we perform the same formula for each element. For the cofactor matrix and adjoint matrix, for 2 by 2 or even 3 by 3 matrix, if A is a square matrix, then the cofactor matrix of A is Cij, where we can obtain the cofactor by this formula. And the Mij is the minor of the element Aij of the matrix A. For the transpose of the cofactor matrix A is known as adjoint of matrix A, and is denoted by, you can write the short form Adj, and is a transpose of the cofactor matrix of A. Look at this explanation. Let's say we have matrix A, the size is 2 by 2. Then the minor of A11, we can say M11. So the M11 is the minor of A11. And the value of the minor A11 is A22 because we close the first row and we close the first column. So the value is A22. And to calculate the cofactor of A11, we can call it as C11. And the formula to calculate the cofactor is, this is the formula, -1 power to the I plus j. For the element A11, the I is 1, the j also is 1. So that's why it's 1 plus 1. And multiply the minor of A11 A11, where the minor of A11 is A22. So we multiply A22. And negative 1 square is positive. Look at the second element. The minor of A12 is the minor of M12 is equal to A21 because you close the first row and second column. The value is A21. And to calculate the cofactor, this is a formula. So we can name the cofactor for A12 is C12 and equal to negative 1 power to the I plus j. The I is 1, the j is 2. And multiply the minor of A12. The minor of A12 is A21. And negative 1 cubed is negative. After you calculate all the value of cofactor, then you assign all the value into the matrix form according to the coordinate. For example, the A22, actually this is a cofactor of A11, so you assign the value A22 into the coordinate of A11. So we call cofactor matrix of A. And to get the adjoint matrix of A, we transpose the cofactor matrix of A. For this example, given matrix A, find the cofactor matrix and adjoint matrix of A. Since we have get the cofactor of each element in the previous example, now we assign all the cofactor value into matrix form. So we call cofactor matrix of A. And to get the adjoint matrix A, and we transpose the cofactor matrix of A. And this is a summary how to get the cofactor matrix of A and the adjoint of matrix A. Look at this example. By using the method of matrices, solve the simultaneous equation 2x minus y equal to 1 and x plus y equal to 2. So I know that, okay, these two equations can be solved by using the substitution method or elimination method. But now, we try to solve by using the method of matrix. So we convert this system, these two equations, into matrix equation. Ax equal to b. So in order to get the xy, we move this matrix A to right side. So will be inverse matrix. So how to get the inverse matrix for the 2 by 2? For example, we have 2 by 2 matrix A, B, C, D. This is the matrix A, B, C. So the matrix, the inverse matrix of A is 1 over AD minus BC and D B C A. So we use this formula straight away, we get the inverse matrix for 2 by 2 matrix. And we multiply, we solve, and we will get the x value and also the y value. Look at this example. Given a system, so we have this system A, write it in matrix equation, Ax equal to b. and find the determinant of matrix A. C. Find the adjoint of matrix A and find the inverse matrix of A and solve the system. For the A part, we have AX equal to B. The matrix equation is AX equal to B. So the matrix A will be the coefficient of X, Y, Z for each equation. And the matrix X is a unknown, X, Y, Z. And the matrix B is constant for each equation. For B part, to get the determinant, we change the round bracket to modulus form. And to calculate the determinant, we call back the sign for each element. For the first element, the sign is positive. And you close the first row and the first column. And we have 1, negative 3, and 2. And you put a cross. And for the second element is negative 2. And the sign for the second element is negative. And still the same method, you close the whole first row and the second column. So we have 3, negative 1, 1, 2, and you put a cross. And same for the third element. And you calculate. So this is the answer for the determinant A. For C part, to get the adjoint of matrix A. Before to get the adjoint of matrix A, we should get the cofactor of matrix A. And after we get the value, then we assign all the value into the matrix form. And you look at the working. Here are the working to calculate the cofactor for each element. And then, after you calculate, so we have the cofactor matrix. And then to get the adjoint, we transpose the cofactor matrix A. So we obtain adjoint of matrix A. For D part, to get the inverse matrix of A, here is the formula. 1 over determinant of A multiply adjoint matrix of A. And here is the inverse matrix of A. For the last question, to solve the system. And our system can be written in the matrix equation, where from the A part, and in order to get the X, Y, Z, we move the matrix A to right side. Make sure before in front of the matrix B. And the inverse matrix of A, we can get it from our D part. And we solve this matrix. And we will get the answer for X, Y, Z. So you can see this example. We solve this example, this system, by 3 different methods. You look at the example with star. Example 1, example 2, and example 8. Look at the last example. The sum of the measure of 2 angles of a triangle is thrice the measure of the third angle. This is the first information. The measure of the first angle is 18 degrees, more than the measure of the third. So based on the question, you have 2 information. Find the measures of the three angles. The question required to get the three angles, but we just only have two information. And you should know, to get the three angles, three unknowns, we should have three equations. Look at the solution on the next page. We let x, y, z represent the measure of the first, second, and third angle. The sum of the measures of the three angles of the triangle is 180 degrees. This is a common knowledge. And based on this common knowledge, you add in one information so that we have three equations, which is not provided in our question. Where the second equation is transformed from our question, and for the third as well. So now we have a system because we have three equations with three unknowns. So we call system. And in the application part, you can solve by any way. Here are the answers for three angles are 78 degree, 42 degree, and 60 degree.